Now, the way that we're going to implement binary search tree is really heavily based on just a normal tree, but there are a few very important differences. Firstly, since we know that there are only two subtrees and the left-right ordering makes a big difference, we're going to explicitly refer to these two subtrees. We're not going to use a list and just say whatever, who cares about the structure of it. We're going to specifically have a left subtree and a right subtree, each of which is also a binary search tree. Another difference between binary search trees and normal trees is in how we distinguish between empty and non-empty trees. So with our normal trees, an empty tree has a root of nothing and an empty list for its subtrees. For the binary search trees, an empty tree also has a root of nothing, none, but its left and right attributes aren't going to be lists. They're also going to be set to none. Even more, for binary search tree, an empty tree is the only case where any of the attributes can be none. When we represent a non-empty tree, we do so by storing the root item, which isn't none, at the root, and storing binary search tree objects in the left and right attributes. Left and right can be empty binary search trees, but an empty binary search tree is not the same as just saying none. Maybe I can illustrate this a little bit by actually building something like that. So here's our old tree code from before. I'm just going to swipe it all away. And here's something that I can do. So I can make a new binary search tree. I guess I need the code from below, but you know what? We'll make it okay for now. We're just gonna build an empty initializer at the moment. Actually, I don't even think we need to. Yeah, we'll just leave it for now. But here is something we can do. We can say B is a binary search tree. B.left and B.right can also be assigned binary search trees, and we'll call them LF and RT, just for fun. RT is also a binary search tree, and we're going to make these both empty. We'll give B, our binary search tree, a root of, 6, just for fun. B.left can be LF, B.right can be RT. Execute. Okay, cool. So, binary search tree is great. We have B is our binary search tree. LF is also a binary search tree, but it's going to be empty. Same with RT, it's going to be empty as well. And our binary search tree is going to have a root of 6. The left subtree of our binary search tree is going to point to LF, which is empty. This is not the same as just none, but it's an empty tree. And the right is going to refer to the other empty tree. So this is one approach to doing binary search trees. Here is how this is different from putting none in these spots. Instead of having these be binary search trees, what happens if I do this? None and none. So note these are represented specifically with the value none. They don't have binary search tree instances. And so when I set up my binary search tree at the root of 6 and I say left is LF, it puts specifically none in here, and right also none. This is not the same thing as what I did before, where I had empty trees on the left side and the right side. And what we're going to go through here is basically making a binary search tree where the only possibility that you have these nones show up is if the whole thing is empty. Now, any method we add to our binary search tree class is going to rely on these properties, specifically that left and right can be empty trees, but they can't just be none with nothing there. This means also that we need to maintain this property, make sure that as we're modifying things, we don't accidentally throw in none where we're expecting a tree. And so this is important enough that we're going to put this in our representation invariance along with the BST property. So here are the things that are going to be true for any of our binary search trees. If the root is none, then so is left and right. This is an empty binary search tree. If the root's not none, then the left and right must be binary search trees, although they could be empty. And the binary search tree property, the reason that we're doing this whole thing in the first place, is that everything in the left side is smaller or equal to the root. Everything in the right side is bigger or equal to the root. So here's the starter code for this class, initializer and is empty, which is pretty much just based on the tree that we've already seen. So kind of unsurprisingly, if the root is none, then everything should be none. If the root is something, then our left and right binary search trees are going to be empty, but they are going to be search trees, just empty ones. And the root is, of course, the root that we want there. And is empty is basically just telling us, is the root none? Now, note that we're not allowing the clients to put in specifically left and right subtrees as parameters. The only parameter we have here is the root. This is because binary search trees have a very strong restriction on where values can be in the tree. And so we're going to have a separate method specifically to insert values into the tree to make sure the binary search tree property is always there. That said, before we get into inserting and deleting things, let's look at the reason that we're doing this in the first place, or at least one of them, which is being able to quickly search for an item. Now, the whole point of binary search with a list is that you can quickly find something by starting at the middle of the list and immediately cutting in half all of the things you need to search through. If what you're looking for is smaller than that, then you go to the left side. If what you're looking for is bigger than that, you go to the right side. So we're going to go for a similar kind of idea for our binary search trees. For general trees, the standard search algorithm is you compare the item against the root and then search into the subtrees until you find the item or you've gone through all the subtrees. When the item is not in the tree, you're going to have to go through everything. Now that's for a general tree. However, with binary search trees, because you have that initial comparison to the root, you can see if you need to go left or right, and you only need to go one of those two ways. So rather than having two recursive calls, before we had a loop because those trees which were non-binary, you could have any number of children, so the subtrees could be a huge number. With binary search trees, because there's only two children, and because we only need to check one way, we can reduce it down to a single recursive call. So contains, this is our algorithm to tell us how to search through. First off is going to give us a false return statement if the thing is empty, because obviously what we're looking for is not there. Otherwise, if it's the root, great, return it. Otherwise, if it's smaller than the root, we go left. If it's bigger than the root, we go right. While this structure really closely matches the empty check for general trees, we also can combine these nested ifs to get a little shorter version. Specifically here, if it's empty, false. If it is the root, we're done. Otherwise, if it's less than the root, we go left. Otherwise, if it's bigger, then we go right.